Okay, in this particular clip I'm going to hopefully explain to you some of the notation for integration and how it connects to the area underneath a curve. Okay, so just to show you basically the sort of question I'm on about. So here we have a function y equals f of x, and I'm interested to know an area. I'll draw this on for you actually. I'm interested to know the size of an area underneath that curve, trapped between the curve and the x-axis, and these limits that are vertical lines between x equals a and x equals b. So my question is, what's the size of this area here? And one way we could approach this is we could say, right, well, I can find an approximation to this. I can try and work this out by splitting it into lots of little strips, which is what those lines are trying to indicate. And if I work out the area of each of these strips, then add them all together, then I'll get a good idea for this particular area. Right, so in this bit I've decided I'm just going to consider one of those strips. And so this strip, I'll just explain its features. This is f of x, isn't it? So this must have a height of f of x, or we said y equals f of x, so it's got a height of y. And I just want to explain this little symbol here. It's a lowercase delta. It just means a little bit of x. And so this is just a bit of the width that I'm interested in. And what we're talking about here is we're going to try and find an approximate area for the bit that I'm interested in. And an easy approximation is to say, well, it's not too dissimilar to a rectangle. And that rectangle would have an area of the height times the width. So there we go, there's the area, y and delta x. So we have to acknowledge though that it's not perfect. And here we can see I've labelled it here as an error. This bit, this is not part of the area I want, but when I calculate this, it will be included. And then we move on from here and say, right, remember this is just one of the strips that I'll be looking at, and I'd have lots and lots of them, and I need to add them all up, which is what this statement is saying. All the ones from A all the way up to B, I need to add all these areas of strips, and that would get me an approximation for this area that I wanted in the question. So the next part of my thinking is to say, what would happen if I let this width, this delta x, get really, really close to 0? Well, one thing that would happen, so I can show you if I split it in half here, one thing that would happen, obviously my strip would get narrower, and there you can see I'd have that error there now, and I'd have more strips because I'd also have to have another one here, wouldn't I? And again I'd have some more error. But what I hope is obvious from where I've coloured it in there is there's less error. So the green bit is the error now. So by having, just even in a simple example, by having twice as many strips, I've reduced the error. So this is the really clever bit now. What if I have an infinite number of incredibly thin strips? Well, that would mean I'd have a lot of strips whose areas I need to calculate. I'd have to add lots of them together, but it also means that this error would get incredibly small. And that brings us on to this notation over here. So that's essentially what I'm writing down here. I'm saying I'm going to let the width get as close as I possibly can to 0. And I'm going to add all of them up. So that symbol there, the sigma, the capital sigma, means add them up. From all the way from A, which was the lower limit, to B, which was the upper limit. And here's the expression for each of their areas. It's their height times the tiny bit of width. And this kind of moves us on to the notation for integration then. Whenever we have this sort of limiting behaviour here, you've seen it with differentiation, these little delta x's become dx's. And this symbol here, it looks like a really long S, and the way I think of that is this is a really long sum to do. You're summing up an infinite number of things, so a long S for a long sum, and that basically explains the notation. Right, so in this one, what I'm hoping to show you is a very specific case, and it's with a function you should know well, and I'm trying to show you that integrating this function is essentially equivalent to finding out the area, or a different way of saying it, finding out the area underneath that curve and between that and the x-axis is the same as integrating the function. So I'll zoom in on the question and zoom in on all these diagrams and try and talk you through all the bits. So stick with it. Okay, so here's the question. It's saying I'm thinking about y is x squared. What will be the area between the curve, the x-axis, and these lines here? And these are vertical lines, x equals 1 and x equals 2. Okay, so zoomed out again, you can see some of these pictures now that I've got and a bit more explanation here. This is our original question. So what would be the area of the curve between the x-axis there and the lines x equals 1 and x equals 2. And this is a diagram of part of that. This is just one of those strips that I'm talking about. So I'd split this into loads and loads and loads and loads and loads of strips, and this is just one of them. Okay, and what I've got here is I've got a little bit of extra detail. So you can see these dotted lines. They are kind of information that's going to help us get to the point where we prove to ourselves that integration is the solution here. Right, what I'm saying is, when I look at this one little strip, I've given it a width here. So if this was x, this is x and a bit more of x, so a bit delta x. So it must have a width of delta x. And it's got a height over here of f of x. So in our case, that's x squared. And over here, it must have another height. And this is x plus a bit more x. And then it must be that squared. Okay, so f of x plus delta x up here. And this rectangle, this little small one, is smaller than this part of the area, which should be what I want to include in my solution. And that in turn is smaller than the biggest rectangle you can see there. So this is the area that I want. This is the smaller rectangle. And this is the bigger rectangle. Right, so what I've written down here is an expression about those things. This is the expression for the area of the small rectangle. This is my label that I've got, delta A, which means just a bit of the area. Because remember, this is just one of the strips, so it's just a bit of the area that I'm after. And there we go, that's that area there. And then this is the expression for the area of the big rectangle. So it's got a height of x plus delta x all squared, and the same width as the little rectangle. And then to get this second line here, hopefully you can see that I've just divided everything by delta x. And what I'm saying here is the little rectangle is smaller than the bit of the area that I wanted, and it's smaller than the big rectangle. And just by doing that division, I've made it look a bit simpler on the eye. And this should begin to look a bit more familiar to you. Okay, so there's that statement again there. And then this is the clever bit. This is really, really good. What happens is I say to myself, to try and improve this accuracy, I'm likely to want to make these strips get as small as I possibly can. So what happens when the width gets really, really close to 0? Well, if delta x gets really close to 0, it shouldn't be difficult for you to think, well, this will be getting very close to 0, which means this bracket would get incredibly close to x squared. And then we have this thing called the Sandwich Theorem. This is brilliant, I really like this. What happens is this expression is trapped in between two things we really know about. And this is x squared, and this is getting very, very, very similar to x squared. And because this is trapped in between them, it tells us that this too must be getting very, very similar to x squared. And that's what this mathematical statement here says. It says, as I let delta x get really close to 0, delta A over delta x becomes a bit more definite, doesn't it? It looks like this thing that happens in differentiation. Instead of writing all this, we just use these symbols to say the limit as delta x tends to 0 of this is x squared. So what we're saying is this thing gets really, really like x squared. And then if you look at this expression, this looks like something that has already been differentiated. So this is saying if you differentiate the area with respect to x, you get x squared. And in Core 1, towards the end of that module, you learnt about how integration is the opposite or inverse of doing differentiation. So if I want to learn about the area, I've got to undo that differentiation. And the process of undoing differentiation is integration. So if I integrate x squared, I get this expression, which is also equivalent to the area. So just to revisit where we've come from with this particular example, this statement here, combined with this and all that proof there, tells us that if you want to know the area between a curve and the x-axis and some limits, then you would need to do it by integration. Now there's a tiny extra bit on here that we haven't finished off, and it's to do with this plus c and the fact that I had some limits to begin with, and we'll look at that perhaps another time, okay? But what we hopefully have shown is that if you want to find the area beneath a curve, you do integration. On second thoughts, I can't leave it till another time. Here we go, I'll show you the actual full solution. So if I want to know this area, this is what I've got to do. I've got my integration, and these are the limits. If you look back at when we had that capital sigma, then there was the limits on there, and they're just the same. What's happened here is I've done my integration, and you'll notice that there's no plus c, and you can get away without plus c when you're doing what's called a definite integral like this. So here are my limits. And when I write them in these square brackets like this, I basically am telling someone that in a moment I'm going to substitute these values into this expression and find the difference between them. I'll just show you that. Okay, there you go. I've put 2 into the expression first, and then I'm subtracting what I get when I put 1 into that expression as well. And there you go, so I've got 8/3 take away 1/3, and my answer is 7/3. And strictly speaking, I suppose it's, because I'm talking about an area, it would be whatever the units happen to be, those units would be squared. Okay, so there you go, that's the answer to the original question, but really my main purpose for this clip was for you to appreciate that if you want to find the area beneath a curve, you do it by integration, or thinking about it the other way around, if you do an integration, it's often the equivalent of finding the area underneath the curve.